today's lecture is on 14.6 directional derivatives. Okay, so what is a directional derivative? Let me start by giving you a recall. df, dx, and df, dy, we say that they are rate of change of f in x or y directions. So this is just in x or y direction, but how does f change when we have when we want to see f in some other directions? For example, in the direction of some vector or in the direction of, for example, z-axis. Okay, so these are also important. So we say, how does f change if we move in any other directions? So in that case, we say rate of change of f, rate of change of f at the point x naught, y naught in the direction of a vector u. We show it by this directional derivative of f in the direction of the vector u at the point x naught, y naught. Okay, geometrically, what do we say? So geometrically, we say that we need to slice graph of f. So slice graph of f by a vertical plane which is basically not necessarily parallel to x or y axis. So if you remember, in partial derivatives with respect to x or y, we slice the graph. For example, when we took derivative with respect to x, we sliced the graph with a plane parallel to the x-axis, perpendicular to the y-axis. And when we wanted to calculate df dy, we sliced the graph by a plane perpendicular to the x-axis or parallel to the y-axis, okay? But this time we slice the graph of f by a vertical plane in the direction of u. Then, so this is the first step, and the next step we say, then slope of tangent line of the tangent line. Let me write it in here. Then the slope of the tangent line to the curve of the intersection what do I mean by intersection? So if we have a graph f like this, and then we slice it by a plane in the direction of, for example, u, then the curve of intersection looks like something like this, right? I mean, the intersection of the plane and of f, intersection of f and the plane. Okay, so the slope of the tangent line to the curve of intersection is the directional vector of f in the direction of u. Okay, good. So how can we calculate that? So this was geometrically. Now, in terms of calculating, we say that we have something like this. We say the f in the direction of u at the point x naught and y naught, and assume that u is the graph, is the vector a and b. It's what? It's the limit of f of x naught and y naught. Okay, but you see, I need to let me write the rest. Minus f of x naught y naught over h, right? And h is the change over h as h goes to 0, and h is the change in the x direction and also in the y direction depending on the direction of u, right? So I should say plus ah plus bh. So you see a little change. So if at the point x naught and y naught, the function is here, and then, for example, u is something like that, we would like to change just a little bit. So x is changing, as you see, plus ah, and y is changing, plus bh, where u is a and b. Okay, so does this look familiar? Let me give you a note. If u as a note, if u is I, the unit vector in the direction of x-axis. So it is 1 and 0. Okay, and in that case, the f in the direction of I is equal to what? It's equal to the limit of f of x naught. So what is x naught? Basically, I'm calculating directional derivative at the point x naught and y naught, right? So the x naught here comes from this fact. So it would be x naught plus, as you see, a here is 1. So 1 plus h, y naught plus b is 0. 0 plus h minus f of x naught y naught over h as h goes to 0. As you see here, this is basically what? This is partial derivative of f with respect to x, because y is fixed. Why not? Why not? Y is fixed and x is changing. Okay, so that is nice. If we take directional derivative in the direction of I, we get partial derivative with respect to x. That was another notation for fx at the point basically x naught y naught. And With the same idea, the partial derivative of f in the direction of j at the point x naught, y naught is basically partial derivative with respect to y at x naught, y naught. Okay, very good. So as you see here, the directional derivative is also kind of like a generalized partial derivatives, because if we take derivative with respect in the direction of I, we get partial derivative with respect to x. If we take directional derivative in the direction of j, we get partial derivative with respect to y. And let me make it 3D. Okay, just assume this function is good. And what is this? The function is this one, z equals to x squared plus y squared. Let me erase these ones. These are distracting. So we have z equals to x squared plus y squared, this one. And you see, I would like to take derivative in the direction of this, for example. So I give you just as an example, just a geometric example. F of x and y is x squared plus y squared, and u is, for example, 1, 1. At the point 1, 2. Okay. The question is this: find directional derivative of f of x equals to that at the point 1 and 2 in the direction of, sorry, at first I wanted to give you like a bullet point example, but I thought that maybe this one is more understandable as the first example. Okay, find directional derivative of this function at the point 1, 2 in the direction of u. Okay, I would like to do that, but before, I'm not going to use definition of the directional derivative, which was this one. I would like to use a formula, but before that, I would like to just show it to you, the graph. So let me graph z equals to x squared plus y squared, as you see here. And then I'm gonna graph the plane in the direction of u. So since u is 1, 1, the plane that is in the direction of u, if you remember equation of the plane, it would be x equals to y. This is the plane. Okay, and as you see that at the point, okay, so this is x and y at the point 1, 2. So 1 in the x direction, 2 in that direction. Okay, at the point 1 and 2, I need to Yeah, so not at the point 1 and 2. In general, okay, at just one point in that plane, for example, okay, at any point, for example, 3, 3, or 3, 4, or 4, 4, okay, at some point, let me bring it up. Oh, come on. Let me just move it like that. Okay. At some point in here, the intersection, the curve of intersection is a parabola. As you see, it's a parabola. And at some point, for example, at the point 3, 3, the slope of the tangent line would give me the directional derivative. Okay. Let me give you the formula. Calculate that. Okay. So we say if you want to calculate that, directional derivative of f in the direction of u is the dot product of two vectors. The first vector is partial derivative with respect to x and partial derivative with respect to y. The second vector is the vector u. But the u that you need to put in here is a very specific u. And what is that? Where u is the unit vector, is a unit vector. I'll write it like that. Is a unit vector. What do I mean by that? I mean, the length of u is 1 if you want to use the formula. How can we, if we want to calculate directional derivative of f with respect to some vector that is not a unit vector, what you should do is to find the unit vector in the direction of the given vector. How do you do that? Well, for example, you're asked to find directional derivative of f with respect to v, and v is not a unit vector. You need to find the unit vector in the direction of v. How do you do that? If you remember, we have v and we divide it by the length of v. And in that case, we get the unit vector. We can also say that u is the vector like this, cosine theta and sine theta. The length of this vector is 1. It's a unit vector where theta is the angle of u with x-axis. Okay, so remember that in the formula you need to put the unit vector. Other than that, you cannot use the formula. Okay, so let's solve this example. Find directional derivative of this function at the point. Okay, so to give you the solution, I know that the f with respect to u, I need to calculate fx, I need to calculate fy. This is one vector. I find the dot product with a unit vector in the direction of the given u. So let me find the u that I would like to plug in here. Let me change this one to v so that the next time that you're reading the lecture notes, you don't get confused. So this is v, and then u is v divided by the length of v. So this is 1 over root 2 and 1 over root 2. Pay attention that this is a vector, this is a number. So it looks like that 1 over root 2 is getting multiplied by this vector. So 1 over root 2 and 1 over root 2. This is the unit vector in the direction of b. Okay, so now what is fx? I'm taking derivative with respect to x, 2x. What is fy? It's 2y. What is the unit vector? 1 over root 2, 1 over root 2. And something else that I need to pay attention is that it says that at the point 1 and 2. So let me find the dot product first. It would be 2x times 1 over root 2. So 2x or root 2 plus 2y root 2. So this is root 2, 2x plus y. Now I'm gonna find the directional derivative at the given point 1 and 2. Just instead of x and y, I'm gonna plug in 1 and 2. So it will be 6 over root 2. Okay. Okay. So I'm giving you 2 notes. This is just calculation. So let's go to 2 notes. Note 1. If we have a function with 3 variables, f of x, y, and z, 3 variables, then the directional derivative of f in the direction of u, you need to calculate the dot product of the unit vector in the direction of u. Just assume that u is the unit vector. And then partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. This vector in here has a nice name, and it's called gradient vector. So this is gradient vector. We're going to use it a lot in chapter 16. So this is called gradient vector. And what is the gradient vector? Gradient vector of f is perpendicular to the level curves. Do you remember the level curves? To the level curves of f. Okay, this is a theorem. For example, on the previous question, the function was what? The function was this one, x squared plus y squared. If you remember the level curves, so to find the level curves, we just slice the graph by z equals to 1, z equals to 2, z equals to 3 by making z equals to a constant. So when f is, make it bigger now, x squared plus y squared, let me, okay, so this is the paraboloid. And if I z equals to 2, let me show it. So as you see, the level curve is just a circle, right? The intersection of the plane z equals to some constant with the paraboloid, okay? And So that was kind of a reminder of the level curves. So the level curves in this example for this function, they are just circles, right? Like this. How do we say that? We say for z, this is z, right? The f here is z. So we say z equals to some constant. This is a circle of radius 1. Circle of radius 1. And then, for example, this one is a circle of radius root 2. You see, this is a circle of radius 2, right? So the level curves are that. So what is the gradient vector for this function? The gradient vector, which is fx and fy, it is 2x and 2y, okay? So as you see, this vector is like that, 2x and 2y. For example, at the point, just assume that this point is 0.11. So for 0.11, I get 2, the vector 2 starting at this point is 2 in the direction of x, 2 in the direction of y, so it would be the vector 2. As you see, this is perpendicular to the level curves, which are circles. Okay, that was about gradient. Now let's look at some applications for directional derivative. So application of directional derivatives. One of them is to find tangent plane, finding tangent planes. So if we have a surface in a space, for a tangent plane, we need to have, for a plane, we need to have a directional vector. And the directional vector here, normal vector. And the normal vector here would be the gradient of f. Oh, my mistake. These are applications of not directional derivative. These are applications of gradient vectors. Of gradient vector. One of them would be to find tangent plane. The other one is to find normal lines. What are the normal lines? Finding normal lines. Okay. So normal lines, basically, they are the lines that are perpendicular to the surface. Perpendicular lines to the surface of F. So in that case, L, the directional vector for the line would be the gradient vector. Let me just give you a recall. Do you remember when we talked about tangent lines? Tangent lines. Okay, we define the tangent lines for a curve in a space. not a surface, right? For a curve. When we have a curve like that in a space, and we said that a curve has a parametric equation, just one parameter, it's just because it's a curve. It's a curve in a space, and r prime t would be the directional vector. Vector for the tangent lines. Remember the tangent line? If we have a curve in a space, we have the tangent line. But when we have a surface, we don't usually have the tangent line. We have tangent planes, right? Because it's a surface. Okay, good. Let me give you an example. Find tangent plane to the surface x squared plus y squared minus z squared equals to 4 at 2, 1, 1. What do you think it looks like? So it was x squared plus y squared minus z squared equals to 4. Ooh. Let me remove this one. It's that. You see, if it was a plus sign in here, then you have a sphere, right? If it was x squared plus y squared minus z plus 4, then it would be a paraboloid. Okay, if it was minus z instead of z squared. Now that you have a z square, it looks like this. Now at the point 2, 1, 1. So 2, 1, 1, some point around in here, some point in here. We want to find the tangent plane. That's the equation. Okay. So to find the tangent plane, what we need to do is to find any plane, we need the normal vector. The normal vector for the tangent plane is gradient. So the gradient vector is fx, fy, and fz. Okay, so what is f actually in here? So you see, every time that I give you some explicit formula, you need to come up with the function. So it would be x squared plus y squared minus z squared minus 4. So the gradient vector is fx is 2x, 2y, negative 2z. So the gradient vector at the point, let me write it like that. I'm gonna bring this one in here, bring everything into here. I'm gonna bring this one over here. Okay, so that's the gradient at the point 2, 1, 1. Gradient vector of f. Plug in 2 in here, I get 4. Plug in 1 in here, I get 2 and negative 2. So 4, 2, negative 2. Now write a plane using this, because the normal vector is 4, 2, negative 2, and also we have a point. The point is 2, 1, 1. So it would be 4x minus 2 plus 2y minus 1 minus 2z minus 1 equals to 0. So this is 4x 2y minus 2z is equal to 8 plus 2 is 10 minus 2 is 8. Okay, let me give you one small note, which would be note 3, I think, because I gave you note 1, 2, and that is note 3. So for note 3, I would like to say that, you see, directional derivative of f in the direction of u, we said that it's the gradient of f dot product with the unit vector u. So when we have a dot product with, if you remember the formula for the dot product in chapter 12, it would be the length of gradient, the length of u, and the cosine theta, which is between, what is theta? It's the angle between gradient of f and u. Okay, so we say that the vector that we're going to put in the directional derivative would be the unit vector. So the length here would be just 1. So we're going to say that the f in the direction of u is maximal. So you see, the directional derivative in the direction of u is just basically the length of f and cosine theta. So the cosine theta is important because you cannot change the length of f, right? So the directional derivative is maximum when cosine theta is 1, because cosine theta, cosine of anything, is between -1 and 1, right? So you see, cosine of anything, cosine theta is between -1 and 1. When we get directional derivative maximum, when the cosine of theta is 1, what it means that the cosine of which angle is 1? The angle 0. So theta is 0, and u, what was theta? Theta was the angle between the gradient and u. So we get directional derivative maximum when u is in the direction of gradient of f. So this is maximum when u is gradient of f. When it is minimum, well, we say that it's minimum when cosine theta is -1, which means that it's in the opposite direction, right? So we say the f in the direction of u is minimal. We should write everything. So the same as before, when cosine theta is -1, which means theta is pi, i.e. this is u, this is gradient of f. Okay, minimum when u is negative gradient of f. Okay, but something else that is kind of nice is that when we get 0, the fu is equal to 0 when exactly the same. Cosine theta is 0, which means theta is 90 degrees. So this is u, this is gradient of f. So when u is perpendicular to gradient of f. Right? So so when do we get this situation? We get this situation, we said what? We said that gradient of f is perpendicular to the level curves. So if you have a level curves for the previous question, for example, that was the level curves. Okay. Then we say that the gradient vector is perpendicular to the level curve, right? Now we are saying that directional derivative is 0 in the direction that is perpendicular to that. So when u is something like this, we get 0, which means what? Which means that we get 0 when we are in the direction tangent to the level curves. So i.e. directional derivative is 0. What does that mean? It means that the rate of change of f is 0, which means that f doesn't change, right? Directional derivative is 0 in the direction which is tangent to the level curves. So indeed, f does not change. Does not change if we move along the level curves. Right? Because along the level curves, how do we get the level curves? We get the level curves when z is equal to a constant. So the function is like constant, right? Okay, so let me give you one example. Find maximum rate of change of f, this function, which is 4y square root of x at 4 and 1. And at which direction does it happen? At which direction? So we say what? The fu is max when we say that we want to find maximum rate of change. So the directional derivative is maximum when u is equal to the gradient of f. Okay. So what is the gradient of f? Is fx and fy. With respect to x, okay, this is constant, I keep it. Now derivative of this one, this is x to the power of 1/2, so it would be 1/2 x to the power of -1/2. And then with respect to y, the rest are constant. So it would be 4 square root of x. Now let me plug in the point 4 and 1. Okay, let me write this one with a more simplification. So it would be 2y and x with the negative exponent. I don't like the negative exponent, so I'm gonna write it like that. Now plug in 4 into here, 1 into here, so it would be 2 over square root of 4, which is 2, which would be 1. Plug in 4 and 1 in here, square root of 4 is 2, so I get 8. Okay, so I have my u equals to 1 and 8. Pay attention that I need to have the unit vector. So the unit vector to use the formula is 1 and 8 over the length. 1 squared plus 8 squared. 8 squared is 64. So this is 1 over square root of 65. 8 over square root of 65. Okay. And the okay, so in that direction is maximum. Max in this direction, in the direction of this vector. And what is, find the maximum rate of change. I need to calculate the maximum rate of change. Oh, come on. I need to turn it off. It's equal to, as you see in the direction, we have, let me bring it down. We have maximum when u is the gradient of f. So it would be gradient dot product with the gradient. Okay. So it would be u dot product with gradient. So it's gradient of f dot product with the gradient of f. Do you remember? Let me give you just a small recall. If we have a vector a multiplied by itself with the dot product, it was the length of a square. Yeah. So it is the length of the gradient square. So the length of the gradient, we calculate that was the gradient. Length of it, we calculated the square root of 65. So square of that, it would be 65. Oh, I'm sorry, my mistake. Because u in here should be gradient divided by the length of the gradient, right? Because I need to put the unit vector in here. So it would be that. So this is just the length of the gradient of f, which makes sense. Why? It's just because, come back into here, it's maximum when u is equal to that, and we say that the gradient is the length, the directional vector is the length times cosine theta. So cosine theta is 1. In that case, we just get the maximum. So this is 1, the unit vector was just 1, so we get the length of f.